I'm Noah Burgum.
I'm Lily Chen.
I'm Sakshi Lande.
I'm Skylar Snow.
And I'm Juliana Zhang.
And our project is designing and simulating a smart COVID-19 air purifier. So today we'll be talking about the problem that we're trying to solve, the product that we're trying to create to solve this problem, both the physical and electronic and networking designs of our product or module, and some airflow simulation to show how our module's impact pans out.
So the idea for this project came from an early COVID-19 outbreak, where a restaurant in Guangzhou, China spread the virus from one person to 9 others. As seen in the CDC sketch, the restaurant's airflow enabled viral particles to travel further than they would have without HVAC. We need to manipulate and purify air to prevent the airborne spread of COVID-19. Our goal is to disinfect contaminated air before it can reach others. And this can be done by using small air purification modules to mitigate the airflow effects of a large-scale HVAC system. These small modules will need to be placed at every table in a restaurant to effectively take in air, purify it, and expel it. However, first we need to sterilize airborne coronavirus particles. Here we have 3 proven methods of inactivating the coronavirus. Copper reacts with microbial proteins and nucleic acids, destroying them in the process. However, this reaction requires hours of continuous contact, making it ineffective against aerosols. Heated nickel foam is a recent development that is incredibly effective against aerosolized coronavirus particles, but its power consumption makes it unviable for portable use. That takes us to ultraviolet C light-emitting diodes, or UVC LEDs, which are effective and energy efficient. There are health risks to radiation exposure, but these can be mitigated fairly easily. To maximize effectiveness, UVC LEDs would need to be used in conjunction with the high-efficiency particulate air filter, or Hepa, to ensure that viral particles are exposed to UVC radiation for the required amount of time. We will be using a 1 watt LED with a 120-degree viewing angle and a 265 nanometer wavelength, which is near the optimal antiviral wavelength. These LEDs are widespread and commercially available in bulk from a variety of suppliers. It will be shining on a Hepa filter, shown in this cross-sectional diagram. This Hepa filter is also widely available from many suppliers.
So a key part of the project was the design aspect. And for our module, we chose to do 3D modeling in CAD, computer-aided design, using the SolidWorks software. Here you can see a transparent image of our module, which consists of a fan, electronics, a filter, and UVC, all contained within an outer shell. The bottom of the module has a set of holes, which allow for air to be intaken and directed towards the filter. Consequently, the top of the module has a set of vents, where purified air molecules can be redistributed into the environment. The dimensions of this module are 110 by 110 by 200 millimeters, which is comparable to the size of a half-gallon milk carton. So at the base of the shell is located a set of electronics, which connect to the UVC LED. Placing the LED at the base of the module lets the cone of light get full reach on the filter, while also containing the light to prevent it from escaping into the surrounding air. Directly above the LED is a Hepa filter, which will capture COVID-19 particles as they enter the module. These particles will remain on the filter until the UVC is enabled, where the filtered air will travel up to the fan for redistribution. Above the filter is the fan, which consists of commercially bought blades and a casing, and is connected to its own set of electronics. The casing holds the fan within the module, and the blades are powered by a built-in motor. As the purified air travels through the filter, the fan blades will capture these particles and carry them to the vents. Here you can see an animation of our fan.
Next is the smart functionality of our system that offers Wi-Fi control of multiple filters on an app. And we use MIT App Inventor to create an Android app that controls the fan and the UVC light with web connectivity to our microcontroller, the ESP32. And as you can see on the left is our app user interface with the blue background organized by table for maximum accessibility with the on and off switch for both the fan and the UVC cleaning light. And as you can see on the diagram on the right, the ESP32, once activated by the app, will send a pulse to the L298 motor driver in the center, which then activates the fan. A similar process occurs with the UVC light, except instead with an electromagnetic relay instead of a motor driver, shown as the blue module on the left corner. Ultimately, the smart system offers flexibility, control, and ease for our users.
In order to visualize the effects of our module, we used two-dimensional Navier-Stokes fluid simulations in Python. Now, that's a mouthful, and so are the equations down there that were used to govern our simulations. But ultimately, here they are. There are two different types: a vector field, which shows the velocities of every particle in the air or every chunk of particles, and the stream plot, which simply connects these vectors to create a bigger idea of airflow. So in order to model the module in this space, we made a constant upward velocity at a given point, which we pointed to here. In order to create boundaries in this space, we found a specific set of points, and we defined them all as having zero velocity, which effectively made them boundaries. Our first experiment looked at the effects of breathing. Okay, so we looked at a person sitting at a table, and with their exhale, you see that the dirty air coming out of their mouth will go directly into the air purifier to be cleaned immediately. Meanwhile, with the inhale, the clean air coming out of the top of the module will go straight to their mouth, and all is well. The dirty air is cleaned immediately, the clean air comes to the person. So there's a clear complementary relationship that we actually predicted would happen. Now, with the sneeze, things were also good. We defined a sneeze as a very high velocity amount of air coming out of a person's face for a small amount of time. So without the module, we saw it started out with very chaotic airflow, but it eventually diffused around the room, creating this big cyclical motion. And what that translates to in real life is a very bad transmission or transmission risk. Lots of COVID particles possibly around the air going to other people, outbreak, bad. With the module, we see a similarly chaotic situation up to 0.4 seconds, which is when the sneeze ends. But after that, it quickly stabilizes the airflow. And by t equals 1 second, shown in the bottom right, the airflow is almost perfectly back to normal. So the module succeeds once again at stabilizing airflow and mitigating the spread. But in order to look at a more complex situation, we looked at a room reminiscent of the Guangzhou restaurant where we had ventilation coming from the left to the right. Here you can see the vents. And we had people sitting on opposite ends of this room at opposite tables. And we asked ourselves, if one person is exhaling on one end and other person is inhaling, is it possible that there's a line of transmission caused by the HVAC system? And what we found is that, yes, there is. The left module shows exactly that and possibly what happened in Guangzhou. This clear line of transmission, which we highlighted in red. But on the right, you see that this line of transmission is very quickly cut off by the module on the table. The dirty air from the person's mouth, as we saw in smaller simulations, goes directly to the module to be cleaned. And there is no more intertable transmission. So we saw it was effective in a much more real-life situation, which was exciting.
To conclude, given a larger time frame, some improvements that could be made would include having more control over the assembly for a physical form of this product. For example, 3D printing each part of the module would allow us to have minute specifications. Furthermore, we could do more advanced three-dimensional airflow analysis to get a more accurate representation of the effects of our module. Finally, we would make plans to expand the app to multiple platforms like the App Store and beta test the UI with users. Ultimately, this compact module can and should be used in conjunction with HVAC systems, and it would successfully catch and kill over 99.99% of COVID-19 viruses.
This project would not have been possible without all the wonderful people listed above, especially Benjamin Lee, our project liaison, and the team at Lockheed for guiding us through this research journey. Thank you to all the sponsors of GSET, as well as Dean Antoine for making this a reality online for the first time ever. And thank you all for listening.